Okay, the last section in this chapter is really looking at rate of change and looking at the differences between this. So we're still looking at linear versus quadratic versus exponential, but we're bringing in some more vocabulary on how to describe what's happening. So our rate of change is really looking at the differences in our x values and differences in our y values. And everything we've done so far has had a constant change in x. Well, what if your x's don't change at that same rate? How can we still analyze that value? And so what we're going to do is we're going to look at the differences in the x values, the differences in the y values, and then we're going to calculate a rate of change. So it's kind of like calculating the slope for each one by taking the y differences and dividing by the x differences. So that way we can compare them. And we do that when the x's don't change at the same rate. So what does the rate of change tell you? Well, if our rate of change is same for every set of numbers, then it's called constant. So this is an important word, constant, which means it's the same value each time. And when that happens, it's going to be linear. Now, if that rate of change is not the same each time, then the function is nonlinear. So it could be quadratic, it could be cubic, it could be exponential. We're not really going to what it is yet, but we're just looking at this idea. Okay, so we're going to go ahead and look to see if it has a constant or variable rate of change. And then we're going to use that idea to determine if the function is linear or nonlinear. So when I look here, I am adding 1 to my x's, and then I am adding 4 to my y's. So that means my rate of change here is y over x. And then I would look and I'd analyze the next set of data. So here I am adding 2, and here I am adding 4. So 4 over 2 gives me a rate of change of 2. And then I'd look at the next one. Here I am adding 3. Here I am adding 0. So 0 divided by 3 gives me 0. And then here I am adding 2. And here I am minusing 2. So this is a negative 2 over 2, which is negative 1 rate of change. So now I analyze, are those rates of change the same? No. So the answer here is it is a variable rate of change. Which means that the function is nonlinear. So now I'm going to go to the next one. I'm going to do the same idea. So here I add 1, and here I add 1. So my rate of change is going to be 1 over 1. So now I'm going to grab another color because I like color coding my stuff. I'm going to add 3. And I'm going to add 3. So my rate of change is 3 over 3, which is really just 1. So we're good so far. So now I'm going to go and I'm going to add 2. I'm going to add 2. So that rate of change is 2 over 2, which is 1. And then I'm going to look at the last one, which is I'm going to add 1. I'm going to add 1, which is a 1 over 1. Sorry about that. 1 over 1, which is equal to 1. Now, since all of those rate of changes are the same, this is a constant rate of change. Which means that this is a linear function. Okay, so this is really falling in line with what we talked about so far, but now looking at when the x's don't have a constant change, how can we still analyze these? Okay, so let's look at this one. So now we're going to be looking at x's and y's. So let's look at our x's first. So first numbers, that's not a very good drawing. So x's, so it looks like I'm adding 3, I'm adding 1, I'm adding 3, I'm adding 3. Okay, So now let's look at those y's. So now I am minusing 3. I am minusing 1. I'm minusing 3. And I'm minusing a 3. So now let's compare those as a rate of change. So we do y over x, so negative 3 over 3 gives us negative 1. And then y over x, negative 1 over 1 gives us negative 1. Negative 3 over 3, negative 3 over 3. Since they are all the same, this is considered constant rate of change. And it is going to be a linear function. So we're going to move on to the next one and do the same sort of idea. So on these ones with these sets notations, I like doing, because otherwise I get confused, I like doing all the x's at once and all the y's at once. So, and sometimes if you want, you could go ahead and do, because it goes y over x, so go ahead and do the x's on the bottom. So here I'm adding 4, here I'm adding 1, here I'm adding 2, here I'm adding 3, and then we can look at those y's. So this is change in x. Now we can look at y's. So here I'm going to add 8. Here I'm going to add 2. Here I'm going to add 2. Here I'm going to add 3. And so now we can analyze that. Well, 8 over 4 is 2. And 2 over 1 is 2. And 2 over 2 is 1. And 3 over 3 is 1. And so now you're seeing that, oh, yeah, it was 2 and 2, and if you give up, you're going to say that it's constant when you really haven't evaluated the whole thing. So always a good idea, go through the whole bit of information so that way you know that this is a variable, it changes, and this would be a nonlinear then, nonlinear function. Okay, so let's use the same idea on this problem. Okay, so we're given some information. We have 2 water tanks. So I'm going to go ahead and look at tank A. Tank A begins to drain, losing half of its volume of water every hour. So at the very beginning, we have 512 gallons. Now after 1 hour, we're going to go ahead and lose half of that. So half of 512, better grab my calculator, is 256, and then we'll lose half of that, so divide by 2, 128, and a third hour, divide by 2, 64, 4, divide by 2, I get 32, fifth hour, divide by 2, and I get 16. Okay, so that's tank A. So now let's look at tank B, and I write really big, unfortunately. Now tank B begins to drain at the same time, but it only loses 40 gallons of water every hour. So at 0, we're still starting with 512. And then after 1 hour, I'm going to lose 40. So 472. And then I lose 40. So 432, and then I lose 40, 392, and I lose 40, 352, then I lose 40, 312. Now, the question they're asking is identify the function that gives the volume of water in each tank as linear or nonlinear. So I can tell that each time I divided by 2 here, that these differences are not the same. So this is nonlinear. In fact, I know for a fact that because I times by the same thing each time, it's going to be exponential. Now this one, because I subtracted the same amount each time, this is definitely linear. Now read the question again. Identify the function that gives the volume of water in each tank as linear or nonlinear. Which tank loses more water more quickly between hour 4 and 5. So they're asking us, what is the rate of change between hours 4 and 5? So here we lost 16 for 1 hour. So that is 16 gallons in 1 hour in that one span of time. Here we lost 40 gallons in 1 hour. So based on the question, which one lost water more quickly in just that 1 hour? And that would be tank B. Now, if you're looking at water more quickly overall, over the whole time, tank A would be it. But you have to read the question carefully. And that's what a lot of people don't like to do. They don't like to take the time to really read the question and understand it, which will get you in a lot of trouble when you go start working in the real world, which is why we try to emphasize that here in high school, we're trying to teach you skills that will carry on to the real world. And if you don't practice them that way, you're going to find yourself out of like 5 jobs before you all of a sudden realize, maybe I should take my time and do it right. And by that time, you have no job references to help say, hey, this is a good worker. This is a person who does the right thing, because you've been fired 4 times. Don't let other people's mistakes not teach you something about how to be a better person and be a better worker and get yourself in a better situation. Okay. Next question, comparing linear functions. So now we're just going to go back to our linear functions. And we're going to look at our rate of change, which is really the same thing as slope. And when we're comparing slopes, those with a higher rate of change increase at a faster rate. Our initial value is also known as our y-intercept. When comparing y-intercepts, those with a higher initial value start at a higher value. So these are just key words that we use to describe what's happening. Increasing at a faster rate or decreasing at a faster rate, starting at a higher value or starting at a lower value. And so we use this to compare situations. So in our problem here, we have Deidre and Beth each deposit money in their checking accounts weekly. Their account information for the past several weeks is shown below. Compare the accounts by finding and interpreting slopes and y-intercepts. So let's look here. Our y-intercept here is 60, and our y-intercept here is 40. So when I compare that, which one starts off with the higher value? Well, Deidre has a higher starting value. Okay, so that's our beginning values, our y-intercepts. So now what we're going to do is we're going to go ahead and we're going to look at the slope, or that rate of change. So let's look at how much Deidre adds to her account each time. So every week she's adding $15. So let's look at how much Beth adds each week. So she goes from 40 to 60, that's adding 20. She goes from 60 to 80, that's adding 20. So each time she adds $20. So who increases at a faster rate? So Beth increases at a faster rate. So we're just describing what's happening. So even though Deidre started with more money, after a while, because she's not adding as much every week, Beth is going to catch up quickly and is going to end up with more money in the long run because she's saving more money each time. Okay, average rate of change for nonlinear function. The slope calculated between two values at an interval. So average rate of change. So instead of breaking it down for each thing, we're only going to look at the beginning and end of an interval to calculate an average slope. So in our nonlinear situation, an investment analyst offers two different investment options for her customers. Compare the investments by finding and interpreting the average rates of change from year 0 to year 20. So I'm really looking at year 0 and year 20, and I'm going to calculate that rate of change. So I'm going to calculate slope, really. So we went from $10 to $32. So when I'm doing the slope, I could say I'm going to start at $10, and then I'm going to look at the difference, and I ended up at $32.07. And most people are like, oh, that's negative, but that's okay. Because when I subtract these, I'm also subtracting these. So it would be 0 minus 20. Now I don't have to set it up that way. I could set it up the other way and we'll end up with the same answer. I could do 32.07 minus 10 over 20 minus 0. The thing that you have to remember is when you're calculating slope, if I use 10 first, 0 has to come first. If I use 32 first, 20 has to come first. So they have to line up like that similarly. So it doesn't matter either way that you do it because you end up with the same answer. If you flip-flop the order, then you're going to end up with a negative answer when you should have positive. And that means that's a huge difference. Some people are like, oh, what's just a negative? Well, that's the difference between gaining money and losing money. And trust me, sweetie, I'd rather get money than lose it. And so now we're going to go ahead and calculate this. So I'm going to go ahead and use the top one, which would be negative 22.07 divided by negative 20. So 22.07 divided by 20, which means that 1.1035, which means that I'm gaining dollars, because remember my dollar numbers are on top, per year. So on average, I'm gaining $1.10 per year. So now we're going to calculate that with investment B. I'm going to use a different color here because I like color coding things. So we're going to start at year 0 to year, what was it, year 20. So here's year 20. Whew! Now the hard thing about year 20 is I have a hard time telling where that's ending up. And that's why graphs aren't always a good thing, but you can really kind of see what's happening. So let's think about slope again, because this is a graph, as rise over run. So I am going up, which is a positive direction, and it looks about like 27. So I'm rising 27, and then I'm running 20. And that allows us to calculate that average rate of change. So 27 divided by 20 is 1.35. So we're gaining about $1.35 a year. Now, is that accurate? No, because that would mean that it looks like this. And that's not truly what our graph is doing. But it gives us an idea that over 20 years, on average, we're gaining about $1.35. Because we get really, in reality, we get a slow growth here, and then it steeply goes up, which is typical for investments. The longer you leave an investment in there, the more money you make in the long run. So in the end of that time, that's when you really start gaining the money. So it's best to start investing early, put a small amount in there, and let it just work its way through time and just don't even touch it. Okay, last problem. Two neighboring schools use different models for anticipated growth in enrollment. School A has 850 students. Okay, School A, 850 students, and predicts an increase of $100 or 100 students per year. So we are starting off with 850 students, and we're going to add 100 students every year. Okay, now School B also has 850 students, but they predict an increase of 8% a year. So I'm going to keep my original value of 850 and I'm going to add 8%, oops, I forgot my 0, 8% for every year. Now let's compare the two models. Well, when we're comparing, I can easily tell that this is linear and this is nonlinear. This is an exponential. Now they have the same starting values, but remember how linear looks like this and exponential will look like this. And so at the beginning, linear will have higher growth. So how did we describe growth, that rate of change? So it increases at a faster rate. So school A at a faster rate at first. But eventually, school B will catch up in their prediction model. And in fact, it will grow faster after a certain point when it catches up. So again, we start off slow, but then we really start increasing. So we get kind of an uptick in here. And so this is just kind of looking at what are the patterns, what's really happening here. Now, this is a little much for you guys, and I may go ahead and ask you, okay, who's higher at this point, who's higher at that point? Because we've talked about how to write these functions. So I'll ask you to write the functions, and I'll ask you to do that, compare those values later on. Something like this, though, these describings may be a little much for you. But again, it's foreshadowing of what you're going to see later on in higher level math classes.